Hey everyone, I'm Jad, the first author of the paper RRAEDy Rank Reduction Autoencoders for Dynamical Systems. And in today's video, I'm going to be explaining the motivation behind RRAEDy, the model itself, and then I'm going to show you some cool video results that we had since we couldn't put these in the paper. In the end of the video, there's also a small code demonstration if you want to reproduce the results. So make sure to stay until the end if you want to code this by yourself and see how RRAEDy works. Before starting to talk about the model, I'm going to start with just defining a certain dynamical system. Say that we have a dynamical system, so anything that changes over time, and this could be anything around us. For example, the way we breathe, or the way I'm presenting to you right now. All of these are dynamical systems because we have a certain quantity that's changing over time. Let's call this quantity alpha. Usually we can approximate or write dynamical system as follows. Alpha dot equal to f of alpha, where alpha dot is our time derivative, and we say that the time derivative can be written as a vector field or a function f of alpha, which is the value itself. Usually we do not have access to this f. All we have access is some data. For example, a video of a certain dynamical system, like some fluid running inside a certain pipe. And so instead of having alpha dot and f of alpha, we're going to have some observations of alpha as follows. So alpha at different times, for example, alpha 1, alpha 2, alpha 3, until alpha t. You could think of this as a video. A video, for example, is such an example of a dynamical system where every frame is basically what happened to the image at a certain time t. And so what we're interested in is a very interesting task. It is time series forecasting. So what we're going to say is, I'm going to give you alpha at a certain time, for example, a certain frame of the video. And then what your model has to do is be able to predict what's going to happen in the video for every time that comes after alpha 1. So I'm going to give you alpha 1, and you have to predict alpha 2, alpha 3, alpha 4, until alpha t. And you could even continue after alpha t to forecast in the future. And this is what we're interested in. This is what RRAEDy can do, forecasting time series, even forecasting to the future. And so to do forecasting, we have many challenges. And one main challenge is that usually, when we observe a certain dynamical system, we do not have access to the alphas. We don't have access to the important parts of the dynamical system. Usually, we have access to X, which is a high-dimensional image or video or whatever curve, which has many unnecessary or unimportant things. And the question is, how can we find a map that takes us from this high-dimensional space to the compressed alpha representation? For example, fluids follow the Navier-Stokes equation. We know that the Navier-Stokes equation doesn't have thousands of parameters, right? It only has a few. But if you're watching a certain video of a fluid going inside a channel, you might have thousands of pixels, right? And so basically, when you have access to the video of a fluid inside a pipe, I need to find what are the important parts that are going to run my differential equations, even though I don't know what they should be. I just know that they should be important to run my dynamical system. So this is the main challenge. If I have a high-dimensional solution, how can I find a compressed representation that is important, even though I have no clue what the alpha should be? The only thing I know is that alpha should be important. And the second question is, if I don't know how many alphas I have, how can I find the dimension of alpha? Do I need the pressure? Do I need the velocity? What else do I need? How many values do I need? And so the main question is, and both of these questions can be summarized in one big question, which is how to find alpha before we try to learn alpha dot is equal to f of alpha. So let's tackle the first question, how to find a map that takes us from x to alpha. What we're trying to do here, we're trying to find a compressed representation by saying alpha should be important compared to x. To think about this, I'm going to ask you to try to remember a nice memory of some nice nature, maybe from a certain hike or just from a certain car trip that you did recently. And if you think about it, you can think about the important things, right? Like how was the general setup, how you felt, probably it felt nice. But you can't really remember all of the details, right? Probably if I put in front of you the same picture right now, with just some small details changed, you will have no clue that I changed something because you only remember the general idea. This is basically how our brains work. The human brain always takes a high-dimensional input X, which is usually images coming from everywhere around us, and it automatically compresses these images into only the important parts that we're calling alpha here, even though no one is telling the brain what's important and what's not. And this is what we're going to try to mimic with our architecture. The first thing we're going to do, just like the human brain, we're going to take this high-dimensional solution, X, and we're going to say there is a function that we call an encoder. It's going to take this high-dimensional solution X, and it's going to find a compressed representation called alpha. So we're going to take this big image that we have and only take the important part. For now, we're saying only take a compressed part, but we still don't know if it's important or not. So how to say that alpha is important, especially that I don't have labels? I have no clue what alphas should represent. I only know that they should be important. Basically, what we're going to say is, if you have these few alphas, these few small dimensional space alpha, you can find another function that we're going to call a decoder that's going to take only these few values of alpha and that is able to reconstruct almost perfectly the big space. Think about it this way. For example, I'm in front of you now. You can see me as pixels, millions of pixels in front of you. If you take only one pixel of my shirt, you can probably remember that my shirt was black. You do not need all of the pixels. And so what we're saying is, if alpha is important, and if I have all of the alphas here, I should be able to decode these alphas. I should be able to find a function that will recreate my high-dimensional solution only using these few values alpha. This is a very popular type of unsupervised learning, which is called an autoencoder. Basically, we have an input, we have an output, which is exactly the same as the input, and we're saying, find me an encoder that's going to compress my data into alpha, and then a decoder that will be able to find, only using the alphas, my reconstructed full space X, and this way I'm sure to find important values called alpha. In this model, our loss function is simply input equal to output. Well, basically, our output is exactly the same as our input, so we don't need to have labels. Now, this solves the first question, which is how to find the map that takes us from X to alpha, but we still have a big problem, which is how to find the dimension of alpha. If I know that I only have 10 important values, then we can just do this, right? Because the encoder is going to take me from the space of X to 10 values, and then the decoder is going to take me from 10 values to the reconstructed space. But how do I do if I do not know the dimension of alpha a priori? I'm just given a video of a fluid running through a pipe, and I want to learn a model that can recreate this video. And the way we do it, we're going to use an enhanced version of autoencoders called rank reduction autoencoder. This model was presented by me and my colleagues last year, and it is similar to a traditional autoencoder with one main difference. Again, we have our input, which is the higher dimensional space X, but now the encoder either increases the dimension or decreases a little bit, but not too much. We're not going to reach alpha. We're going to reach a space that we're going to call Y, which is a bit bigger than alpha, or maybe a lot bigger. What's important is bigger than alpha. And what we're going to say is, once we have our space Y, which is our latent space, we're going to perform a truncated SVD on this. Don't worry if you don't know what an SVD is. Basically, the SVD gives us two things, a basis that we call U, and coefficients that we call alpha. And what's important about the SVD is two main things, two main properties. The first property is that there is what we call the truncated SVD, and the truncated SVD can find a compressed representation. So instead of having Y, if I take the truncated SVD, I can find a certain reconstruction of Y called YK star. And it's really nice because YK star and Y have exactly the same dimension, so they have the same length, but YK star is only represented by a few alphas. And so basically what we do is we remove the limitation of depending on alpha, because both Y and YK star do not depend on the dimension of alpha. They have the same length. It's just that the alphas are hidden somewhere in the middle, but we do not see it. And so basically the encoder only sees Y, which is a big dimension. It does not see alpha. And the decoder only sees YK star, which is again a big dimension. But this YK star can be represented by the alpha K star, which is somewhere hidden in the middle. And so the decoder by itself does not see the dimension of alpha neither. And so basically this is really interesting because now that our model does not depend on the dimension of alpha, we can ask the model to find alpha by itself, because now we can change alpha easily without having to change the architecture of the model. This is what we introduced in our paper, Rank Reduction Autoencoders. So this is an older paper from last year. And basically the adaptive algorithm goes as follows. We go with the architecture that you can see on top here. We have the alphas that are hidden inside the latent space. So both the encoder and the decoder do not see the dimension of alpha. And what we're going to do, we're going to train as follows. First, we say take the biggest dimension of alpha that you can. Since we're doing an SVD, the alpha cannot be infinity. So you take the maximum dimension of alpha that you can. And then you train until convergence. So you train as much as you want. Now that you have a converged model, what you're going to do, you're going to start removing the alphas one by one. So a second important property of the SVD is that it sorts the alphas for us. The first alpha is the most important, the second alpha is the second most important, etc. And so basically when you train with all of your alphas, once training is done, what you can do is continue training after removing the last alpha, because you know the last alpha is the least important. So you remove the last alpha and you continue training for a little bit. So you reconverge. Then you remove the last alpha, and again, you repeat and you repeat and you repeat. Every time you remove one value of this vector alpha, and you continue your training, at some point, your autoencoder will not be able to converge anymore, and you will see a very strong jump in the loss. And this means that you went too far. You reduced alpha too much, and it means we can determine what is the dimension of alpha because the adaptive algorithm is going to stay at some point. Listen, you went too far. You cannot go, for example, to 2 values of alpha. You're going to need 3. For example, that's how the training loss looks like when training a rank reduction autoencoder using the adaptive algorithm. So we trained first until convergence, and then every red line means the adaptive algorithm removed 1 value of alpha. And as you can see, every time we're going to have a small jump. The jump is not too big because the last alpha is the least important. We're going to continue training, and so this jump is going to go back down, and we're going to reconverge to our optimal loss, which we found before. We're going to keep doing this again and again and again. And here you can see that obviously 2 was too much because we just jumped to 120%. And then we never really converged to the optimal loss again. So you could have guessed from here that basically 2 was too much, and the number of alphas that we need are 3. And so now we solved both of the problems by using rank reduction autoencoders with the adaptive algorithm. We know how to find alpha from X, which is a high-dimensional solution, and also we know how to find how many values of alphas are important. Now that this is over, we're going to go with the most important question, which is, we have alpha, how to find or to learn f of alpha? Because what we want to do is forecasting. We want to make alpha move over time, and so we want to learn alpha dot, which is f of alpha. So how to learn f of alpha? Again, this is the model that we have for now. The alphas are here in the latent space. We know how to find them. We have 2 main ways to learn a dynamical system. I like to call them structured and unstructured ways of learning a certain dynamical system. Structured could be anything where you specify how the dynamical system should look like. For example, a SIND, where you specify a dictionary and you say it has to be a linear combination of this. Or a DMD, where you say it just has to be exponential or a linear evolution. On the other hand, there are unstructured techniques where you just use neural networks to learn f of alpha. For example, neural ordinary differential equations or recurrent neural networks. For us, since we use neural networks to be our encoder and our decoder, we assume that these are strong enough to be able to learn any structured representation of alpha that we're going to enforce. And so we're going to go with the most simple structured representation, which is the dynamic mode decomposition, the DMD. If you don't know what it is, don't worry, because I'm going to go over a very small background so I can introduce the notation of the DMD. The DMD works as follows. You have a certain alpha at a certain time, alpha t, and then you have alpha at the next time, which is alpha t plus 1. The DMD assumes that we can find an operator w such as we approximate alpha t plus 1 as w times alpha t. So you have a w, and advancing the system in time is very simple. You just multiply by w. If you multiply alpha t by w, you get alpha t plus 1. You multiply alpha t plus 1 by w, you get alpha t plus 2. And so basically the way we find this operator w is as follows. We're going to define alpha to the power parenthesis t, which is basically all of the alpha values going from alpha 1 to alpha t minus 1. So we're going to take alpha at every time step except the last one. And then we're going to take alpha to the power parenthesis t plus 1, which is going to be the matrix where we put alpha 2 until alpha t, which is the last value. And so what we did, we took our matrix of alphas that we had before and we just shifted by 1. And so now our DMD operator can be thought of as this. We're going to take this w, we're going to multiply this big matrix, and basically multiplying w by this matrix is exactly the same as saying I multiplied alpha 1 by w, I multiplied alpha 2 by w, I multiplied all of these alphas by w. And so basically what we want is, anytime I multiply any of these by w, I'm going to have the shifted version. So the time t plus 1, which is this value here. And so basically what we're trying to say is alpha t plus 1 as a matrix now is equal to w times alpha t as a matrix. Now, the equal is a very strong statement here because usually you cannot find a w such as this is exactly equal. So we're trying to do an approximation. How to find the best w such as we can approximate all of our alpha t plus 1s using w times our alpha t's. Basically, the mathematics tell us that we can find this w by doing this. It's alpha t plus 1 times the pseudo-inverse of alpha t. We're not doing an inverse because usually alpha is a rectangular matrix, and so usually the inverse doesn't even exist. So the pseudo-inverse is the best approximation that we can do in this case. When we find this operator w, what we can do is the following. We can do forecasting by saying, listen, give me the initial condition, which is alpha 1, and then I'm going to multiply by w, I find my approximation of alpha 2. I'm going to multiply by w one more time, I find the approximation of alpha 3, etc., etc., etc. And so finally, w to the power t minus 1, so multiplying by w many times, t minus 1 times, and multiplying by alpha 1 is going to give me alpha t minus 1. And so basically, if I learn this DMD, if I learn this operator, I can use it to forecast values of alphas. And this is what we're going to call alpha tilde. Alpha tilde is basically our approximation when forecasting using the DMD. Now that this is explained, I can finally present to you RRAEDy, our model, rank reduction autoencoders for dynamical systems. Our model, RRAEDy, is as follows. Again, you have an autoencoder where you have the input x and the output, which is again x. So input equal to output, just like before. Then you will go through an encoder, just like rank reduction autoencoders, to a space y. Y could be bigger than x, or it could be smaller than x, but what's important is it is bigger than alpha. So choose a value that is just bigger than the maximum alphas that you might have. Once you have y, you're gonna perform a truncated SVT in the latent space to do the final compression using the SVD. And so now you're gonna have the basis u and the coefficients of the SVD alpha. And now we're gonna perform a DMD, and we're gonna do forecasting using the DMD to find the alpha tilde. And this is where it is very important, and this is where RRAEDy is special. We do not put any lost terms that are going to say alpha tilde are close to alpha. What we do is we replace the alphas by the alpha tilde that we have here, and then we pass the forecasted values of alpha tilde multiplied by the basis to the decoder. And so it is very important to note that we do not pass the alphas to the decoder. The decoder never sees what's generated by the encoder. We only pass the forecasted values of alphas. And finally, once we have the output, we're simply going to say, again, the loss function is output is equal to input. And so it is really nice because RRAEDy only has one loss function. So optimization is very easy. You do not have hyperparameters to fine-tune, especially in the loss function. Of course, you have model parameters. And so basically, what we're saying here is, if this architecture converges, these alpha tildes should be nice and should be good. And so if they're good, probably we're not oscillating anymore. If we're not oscillating, it means alpha tilde are close to alpha. And so we do not need to put any other loss terms. We do not need to put the eigenvalues or eigenfunctions of the DMD. We simply say, replace our values generated by the encoder alpha by the forecasted values, which are alpha tilde. And this is also nice because we're not enforcing the decoder and the encoder to do just the inverse functions of one another, because we're saying the encoder is going to generate alpha. I'm going to give the decoder alpha tilde. So at the beginning of training, probably the encoder and the decoder are going to do different things. And then they're going to converge slowly to doing the identity function or the inverse functions of one another. And this is why RRAEDy converges really well, because starting from the beginning by saying the encoder should be the inverse of the decoder can be problematic. It can lead to local minimums. Now, this is how RRAEDy looks like when we perform training. So we do an SVD and we do a DMD. However, when we want to do inference, RRAEDy is a nice model because you only have to do matrix multiplications. You do not have an SVD anymore. You do not have a DMD anymore. You replace them by their equivalent using matrix multiplication as follows. Once training is done, you're going to compute a common basis that we're going to call UF. So as you see here, U is just the basis that you find during training. And so if you're doing batches, every batch that you're going to have is going to have a different basis U. So basically, after training, you can find a common basis, UF, as presented in the paper, and you can find a common DMD operator W. So the W that we had here for batches, now you can find a common W operator there. And so in inference, when you want to do forecasting or when you want to evaluate the model, when you give x at a certain time t, either initial condition or just a random time t, and you want to do forecasting, first you're going to go through the encoder to find y at a certain time, so yl we're going to call it here. Then you're going to replace the truncated SVD by the multiplication of UF transpose. Basically, if you multiply by U transpose, it's like you're doing projection on a basis, and this is exactly the same as doing an SVD. It is the approximation of it, actually, to find the certain alpha. So this is how we find the alphas, by multiplying by U transpose in here. Now that we have the alphas, we're going to use the W to do forecasting by simply multiplying by W many times, like we explained before in the DMD. And finally, I re-multiply by U to go from alpha to YK star, and then I can decode. And so when I decode, the number of times that I apply W is basically the number of time steps that I'm going to have in the future. And so now we have this model where we can do forecasting. You just give X at a certain time T, and then using the saved values of UF and W, you can just forecast in the time as much as you want. This is RRAEDy, and basically RRAEDy has many advantages. The first and very important advantage is that we discover the dimension of the latent space automatically. You do not have to say, I have 10 values, I have 15 values, like you do in many or most other models, but basically RRAEDy can find the dimension of alpha automatically when you do training. Second, we impose a linear evolution, and we like to stay in the linear evolution state because it's easy, it's nice, and we can study the stability and all of this. Third of all, it is easy to train. In our model, we never change the architecture. So when we have a CNN, we had fixed CNNs, we never changed them. In MLPs, we also have fixed hyperparameters. And so tuning hyperparameters in RAEDy is very simple, and especially because we have one loss function. So optimization is easy, and the loss function usually decreases relatively fast. Fourth, we avoid learning the inverse operator from the start. In the end, we converge to an inverse operator, but not during training, and this means convergence goes even better. And finally, we have regularized dynamics. The reason why we have regularized dynamics is because we're doing the DMD on the coefficients of the SVD alpha. And basically, because we're doing so, as you can find in the paper, we have two theoretical proofs or theoretical guarantees. First, we say that all of the DMD operators W that we find for batches, they are similar, which means when you train over batches, you do not have instability. Your loss isn't really expected to jump because the matrices are similar. And so finally, we're going to converge to a nice set of matrices which are going to work for any batch. And this is why we can find a common operator W at the end of training. And second, and again, it is because we're using a rank reduction autoencoder, so because we're using an SVD before doing a DMD, we could prove that W converges to the identity and that this convergence depends on K star, which is the dimension of alpha. So let me explain. If alpha is very big, W is far from the identity. So the autoencoder, or RRAEDy, is able to explore W's and to just find any W that it wants. So first we have maybe some oscillations, or the loss doesn't really decrease or stagnate. But then, the more our adaptive algorithm removes values of alphas, the more this bound is tight, which means W becomes closer and closer to the identity, the more we go further with our adaptive algorithm. And basically, by the end of training, our W is going to be very close to identity, and so we ensure that we're going to have marginally stable dynamics. It's not perfectly stable, it's marginally stable, but then we show in the results that this marginal stability actually works very well. Our model never explodes. We do not go very far from identity because of this bound that we have here. Now what I'm going to do, since I explained the model, I'm going to show you some of the results using some videos. The first one is going to be on the van der Pol oscillator. Most probably, most of you have already seen this oscillator before. And this is nice because we have a limit cycle that repeats itself. And so basically, we can see if we can extrapolate to the future. And so now in the video here, you could see, if I choose an initial condition to the left, which could be any value on the square there, then you can see that our model, which is here only taking the initial condition and advancing the system over time, it is able to accurately predict the entire states of the system, given only the initial condition. So here what we gave is only this point here, the first point, and this point there, the first point. And using UF and W, what we already memorized in the model, we can forecast the system over the training range, as you can see, even though this is a test set because the initial condition was not given before. But also we can forecast to the future, and it is stable. We do not explode. You don't see any unstable behavior because basically we showed that we have marginal stability when using RRAEDy because of the rank reduction autoencoder part. The second problem that I'm going to present is Berger's equation. So Berger's equation has some shocks, and usually you're expecting to see both diffusion and advection. And as you can see here, so what I'm doing, I'm changing the initial condition by changing the parameters of the polynomial function. And then when I press on run, as you see, for a different initial condition, I press on run, and now we use UF and W, and as you can see, the orange and blue are basically on top of each other, which is our prediction and the new simulated value. So one more time, RRAEDy can extrapolate on different test sets because these initial conditions have never been seen by the training set, but also it can usually forecast in the future, which we could not see here, but we could see on the van der Pol equation before. The third problem, we're going to use CNNs because now we're going to use images. So before we were using MLPs, fully connected networks. And here we're going to use the problem of the fluid behind the cylinder, very classic, where we use the Navier-Stokes equations and we fix some boundary conditions. And this is when I change the inlet velocity, how the model can extrapolate in time. So it can forecast in time. And basically the inlet velocities, one more time, they could be new. They could be different from the ones we see in training. And as you can see, the forecasting goes really well, which shows how RRAEDy can learn on a certain training set and can extrapolate on others and can also forecast. The final example is one that's very challenging for autoencoders because it is very localized. What we're going to say is we're going to take a certain Gaussian function, so very localized because it's just the Gaussian and the rest is just zeros. And basically this Gaussian is going to do a dynamical motion, which is rotation. And so it is a nonlinear motion since it is rotation. And basically it's very small, so it's localized. And on this example, RRAEDy was the only one to perform well compared to all of the other variants where we remove parts of RRAEDy, as I'm going to explain later. But this is how RRAEDy works. So I press anywhere in the image, and as you can see, RRAEDy can rotate the Gaussian by itself. And it works quite well, even on localized examples, especially because our alphas are regularized because they come from a rank reduction autoencoder, and they have to follow a certain linear dynamics, so the dynamics cannot go very wrong or it cannot generate artifacts. So I've presented some of the results that show that RRAEDy can be trained on different types of curves or even images, and it works quite well, it is quite stable. But I added many things to get to the model. I added the DMD, I added the SVD, I added the adaptive algorithm. And so one might wonder, are all of these parts necessary to get this stable, good model? And so what we did to show that it is actually needed to do what we're doing is an ablation study. You can see the details in the paper, but I'm going to present some of them here. So again, on the rotating Gaussian problem, you can see now in images, so you cannot see the rotation anymore, but only the position at different times. The true values are in the top row. The second row shows RRAEDy, which is almost perfectly well. We cannot see the difference between both here. And what we trained in the last row is basically exactly the same as RRAEDy. So with the DMD and everything, but just without the rank reduction part, which means without the SVD. So we did the DMD on the alpha space, and we said we assume we know the alpha space, which is the one that we found using RRAEDy. And basically we just trained without the SVD. And as you can see, we have artifacts. So we do not have only the Gaussians, but some things that are randomly generated around the Gaussians or somewhere else in the image. And this is basically because the alphas are not regularized in an autoencoder with the dynamical mode decomposition. And so basically this shows how important it is to have the SVD in the latent space. Also, in this table, I show the errors for different variants that we did. So in the second column here, we used a fixed RRAEDy. So basically, again, the RRAEDy model, but now we don't use the adaptive algorithm. And as you can see, sometimes we get stuck in local minimums. So here the error is almost twice as large. And this is because, so if you remember, I said W gets closer to the identity, the smaller the alpha is. And so in a fixed RRAEDy, alpha is small since the beginning. And so W always stays small to the identity, and so sometimes you get stuck in the local minimum. On the other hand, when we don't do the DMD or when we don't do the SVD, we can see that the dynamics are unstable. Sometimes we get 100% error, sometimes we get local minimums. And the only model that works correctly is our variant with all the SVD, the DMD, and the adaptive algorithm, which shows that we actually need all three components for RRAEDy to work correctly. Up until now, we only talked about differential equations that look like alpha dot is equal to f of alpha. However, in real life, there might be more complex differential equations. For example, those that depend on a certain parameter or many parameters. For example, we can write this as alpha dot equal to f of alpha mu, where mu is a vector of parameters. In this case, we will have to modify RRAEDy to take into account the parameters as well. And basically, we included this in our paper just to show that RRAEDy is very flexible in terms of architecture. So when you want to modify, for example, to do controlled differential equations or to do equations that depend on parameters or whatever you need, you can just do it using RRAEDy by modifying slightly the architecture. For example, when we have a dependence on a parameter, an example of a model architecture that we could use is as follows. We're going to do exactly the same thing as before. So we still have the SVD part, the DMT part, and the decoder, which is here. We still have the encoder, just like before, that gets us to Y. But what we're going to do, we're going to slightly change the model and say, we're going to have the input mu now as a parameter into another encoder. So we're going to get Y mu. And so now not only we're going to have Y that's coming from X, but also Y that's coming from the parameter. Since the parameter is fixed, we're going to just repeat this parameter many times. So repeat the mu many times, which is assuming that Y mu is always the same because mu is not changing over time. So if you have parameters that change over time, you would just remove this repeat operation and have a time series that's coming from the parameters that are changing. And basically, the only difference that we did is we're going to take the Y that's coming from the X and Y that's coming from U, and we're going to concatenate these, repass them through a small encoder part, just to say mix them a little bit. It's a fully connected network. And then we're going to do the SVD. And so now the SVD and the DMD not only depend on X, but they only depend on mu. To show that this simple, introduced, modified architecture can work, we just took a mass spring system with different parameters. And here you could see in the simulation, when I change the parameters of the mass spring system, our prediction is always quite good. So we have a nice approximation wherever I go. And these are, of course, test values because we're just choosing random values on the buttons that you see there. And so basically here, we're giving the initial condition as an input, but also giving the three parameters. And what you can see in the example is that giving only the initial condition and the parameters, we can find a matrix W and the basis UF, such as we can reproduce the entire system and forecast over time. And this shows also that RRAEDy is flexible and you could just modify it slightly to have more advanced versions, like for example using a DMDC or just adding the parameter like we did here. These were the main results, and so as some conclusions before I go to the code, we proposed a model that can do forecasting, so either forecasting along the training horizon or also forecasting to the future. And you have many guarantees, which are the stability, the linear ability, and all of these are only using one loss function. This is why the training goes easy and fast. We do not have lots of hyperparameter tuning. And finally, the model can be easily extended, for example, to have parameters or control differential equation. And finally, the part I'm going to discuss now is the code. The code is open source, and it is in a repository that is called RRAEDy. If you're staying for the code, I'm going to now switch to my PC view, and so we could code together and see how we could use the repository to either train RRAEDy on some of your examples or also evaluate it and see how you could forecast using the model architecture in JAX. Okay, so for this part, I will be sharing with you my laptop screen, and I will be showing you how to get the code and use the code on your own PC. I'm going to be using Windows, so if you have different operating systems, you might need to do some small changes, but usually everything is going to be very similar. So I will start by creating a folder on my PC, and I will call this folder RRAEDy. And then the first step is to get the code for the RRAEDy repository, which we're going to do by going on Google Chrome or your preferred browser, and then going to github.com, my repository, which is JADM133 and RRAEDy. I'm going to put this in the description. And then you're going to get the code. So you have two ways of doing it. Either you can download it as a zip file here, or you could just get this using HTTP or SSH if you have SSH set up. I'm going to do it using SSH. So I'm going to open Visual Studio Code, and then open this folder that I just created, so RRAEDy. And then I'm going to go to my terminal and say git clone, and then use the SSH link that we had. And so this is going to clone the repository to my folder. So again, if you don't have SSH set up, you can just go there and say download zip, and then the zip file that you're going to have is going to be exactly this, RRAEDy, that you have here. And so now that you have RRAEDy, we still have one thing to set up, which is the library rank reduction autoencoder. So that's another library in another repository that you can see here. So again, JADM133 and then RRAEs. I will also put this in the description. The good news is that this is now an installable library. So what you can do is just go down and see that in the README, there's a function to install. I'm going to use this one to get the most recent changes. And so basically, you can write pip install git plus, and then you write the name of the repository. And this is going to install rank reduction autoencoders for you. This library is the basis of the code that we're going to use for RRAEDy, as you will see later. So you just need to pip install it. As you can see, I have already all of the requirements satisfied. If you don't, it's going to install the important libraries for you, like Equinox, JAX, whatever you will be missing. And so once you have this RRAEs set up, now I'm going to show you some parts of the code. So first, there are many scripts, as you can see here. Script CNN is going to train a convolution neural network. So if you have images or a video, then script MLP is going to be just a curve that changes over time, like Berger's equation that I showed before, or the van der Pol. And finally, script param is when you want to give parametric inputs in the modified model that I showed you. Then all of the plot functions is for you to generate the same plots that we did in the paper, if you're interested to see how to generate these plots, or maybe use them in other examples of yours. And so I'm going to show you some parts of the code. Let's start with script MLP. Basically, the first part, which is from here to here, is us getting the data. So I have a function called getData that will get van der Pol, Berger's equation, everything that I just presented. If you want to generate your own data, you can do it. You just need a NumPy array of this shape. So d times t times n. D is the number of features. So if you have position velocity, this is 2. If you have a curve, it's going to be the number of mesh points on this curve. And then t is the time dimension. So the curve at each time. So when I put 0 here, I'm going to get initial condition. When I put 1, it's the time step after and then after. And finally, n is the number of samples. So for different initial conditions, how many curves do you have? That's the shape of your data for script MLP. I'm going to show that for CNN, it's quite similar, but with some changes. Here you define your data, and then you have some default values here for ptrain, ptest, because basically we don't use these, but you have to specify them for rank reduction autoencoders. Then you will choose the method. This name is only to save the file later, so you could choose it to be whatever. Then if you set rank reduction to true, you're gonna do the SVD. If you set it to false, you're gonna remove the SVD if you want to do some ablation studies. Then if you set just pass to false, it's gonna do the DMD. If you set just pass to true, then it's gonna just pass them through the network, so without doing the DMD. And again, it is only for ablation studies. So usually you can leave these to true and false, and this is gonna do RRAEDy. Then for your model class, you could use any class that's already defined in rank reduction autoencoders. But since we imported in the first line of the file here, RRAEDy.config, it's gonna set the configuration such as any model, any class inside RRAEs is now gonna become a RRAEDy architecture. So RRAE MLP in this case is just gonna be an SVD and a DMD while using MLPs as an encoder and a decoder. On the other hand, if you go to script CNN, you will see it's a very similar script, but now with RRAE CNN. And so basically, we're going to use this model in this case because we're using MLP. And then we're going to specify the latent size and Kmax. Latent size is how big you want your Y vector to be. So remember, your Y vector can be anything as long as it is bigger than the maximum amount of alphas that you might have. So if you think you might have 10 or 20 alphas, you can set the latent size to 100, and then it should be fine. And then Kmax is the initial Kmax value, so the initial length of alpha. This is what Kmax means. And so if you set Kmax to 9, I'm going to start with 9 values of alpha, and then the algorithm itself is going to decrease it slowly. Choose this to be the biggest number, which is usually either the latent size or the batch size, because these are the 2 dimensions of our matrix. So choose Kmax to be the minimum between the latent size and the batch size. This is usually the best practice. Then we define our trainer class. This is from the library RRAEs, which is going to do the training for us. We're going to map twice, because once we're going to vectorize over the dimension n, so the dimension of the samples, and the other time we're going to vectorize over the dimension t. And so basically, if you're using GPUs or TPUs, this is going to run fast because it's going to vectorize the entire thing. Here we have the loss function, and as you can see, so the model is done in a way that when you call the latent function, you can give it rank reduction and you can give it just pass, so it's only to do the ablation study. But otherwise, it's very basic. We just do the latent and then we do decoder, and then our prediction is simply this norm loss. I like to use personally the norm of the difference divided by the norm of the true value times 100, because it's a percentage, so you're sure if it's good or not. When I say 1% or 2%, for example, compared to 100%. But feel free to change this to whatever you want. It takes X and Y as true value and a predicted value, as you can see it here. And finally, we have the training arguments, where you could specify the step strategy, so how many forward or backward paths you want, the batch size. So be careful if you're on CPUs, this is going to run very slow because JAX is not optimized on CPUs. And if you're using Windows as well, you cannot really parallelize over GPUs or TPUs. So I advise, if you want to use this code, to either run it on a virtual machine, Linux, or run it on Colab, or on your machine if you have a Mac or a Linux operating system. Otherwise, reduce the batch size for you to be able to run the experiments on Windows. Then the learning rate strategies. So you can give many. If you give many learning rates, many batch sizes, and many steps, it's going to do, let's say, 100 steps with a batch of 64 and then E-3, and then 100 steps with a batch of 64 and a learning rate E-5. So you can do multiple trainings here. And then basically you can keep the rest the same. This is the tracker, which is going to do the adaptive algorithm for us. And if you know what is the perfect loss that you can achieve, you can put it here. If not, you remove it, and the algorithm is going to choose it automatically. Then this is how much I wait before starting the algorithm, because you just want it to converge really well before you start checking if you stagnated or not. And basically, this patience is to say, is the Kmax that I arrive to too small or not? So the bigger this is, the bigger the algorithm is going to try to go for a Kmax that's small before saying, no, this is too much. If you know the minimum Kmax that you can get to, you can specify it by saying Kmin here. Otherwise, you can also remove it. And finally, the converge steps is, once I converge to this minimum Kmax, if you gave it to me, how many steps should I do afterwards? So both of these values, if you don't know what is the Kmin that you can reach, just remove them and the algorithm is going to determine them automatically. Finally, this is for fine-tuning. So in the original paper of rank reduction autoencoders, we propose that we can fine-tune the basis that we find after the training is done. But usually you don't need it, so just keep this to 0 and everything is going to be fine. You're just going to perform training without fine-tuning. And finally, with one simple sentence, you can perform training by saying trainer.fit. You just give the inputs and the outputs. In our case, they are exactly the same. Xn and Western are the same. You give some random keys because this is to define the initialization of the optimizer and everything. And then you give your training arguments, fine-tuning arguments that you gave before. And this pre-func imp and pre-func out are there for you to do stuff, some functions on the batches, in case your data is very big to be loaded on the disk. So if you don't want to load the data, let's say as floats, you just want to convert to floats during batching, you can do it using these pre-functions. If your data is not that big, you don't need to worry about those. And finally, when you say trainer.save model, you will save the model in a certain file here next to your script. Now, if you want to perform predictions, you can give only your initial condition, as you can see here. So I give only from 0 to 1. Now, be careful not to remove the dimension. So the dimension has to be there. This is why I say from 0 to 1, and I don't say 0. Because if the dimension is not there, the encoder is not going to understand where did the dimension go. So you have to give from 0 to 1. Here, I only gave 100 samples in case your samples are very big for the model not to explode the memory. And basically, what you will do is apply basis is trainer.basis. So this is the UF that was already saved in our trainer. And we're going to give it as apply basis. And we're going to say apply W is trainer.w. So again, the W was saved in the trainer when you did trainer.fit automatically. And so now when you say apply W, it will apply the W in the DMD instead of performing the DMD itself. As you remember, because in evaluation, we need to apply these Ws and apply the basis instead of performing the SVD and the DMD. And since we're applying W, you can decide how many steps you want to apply it to. So you can forecast to go as long as you want. And so in this case, I'm just going to say forecast as much as the shape of our training. And generally, you can forecast more and see what happens. And this is your prediction. And so your prediction is going to be of the same shape as your input, which is d times t times n. And if you specify your t to be bigger or smaller in steps down there, you might have longer or shorter series. Because now what's nice is that with RRAEDy, you can choose how many time steps to go in time. So you can do it by yourself. Now I'm going to go to script CNN, where you're going to see that it's actually very, very similar to the other one. Except only the difference here, where now the shape of our input is C times H times W times T times N. So the last two dimensions are still the same: number of samples, number of time steps. But now the C is the number of channels. So if you have grayscale, it's going to be 1. If you have colors, it's going to be 3. If you have F number of important things on every pixel, it's going to be F. And then H and W are basically the height and the width. And since we are importing, again, RRAEDy.config in the first sentence, here, when you import RRAE.cnn, it's going to be automatically doing the SVD and the DMD for you. So again, you can define the trainer. Now, if you want to define some specific aspects of the model, let's say the number of hidden layers, the kernel size, you can do it also here in trainer. You can find all of this documentation in the rank reduction autoencoders library, but I'm not going to go over it here. Usually, you don't even need to change the architecture. The architecture that we're using, we're seeing that it works everywhere. Hence, you don't need to fine-tune the parameters much. But of course, if you need to change the activation function and all of this, you can do it. You just need to go to the documentation of rank reduction autoencoders. Again, so we define the last function and all. And as you can see, it is very, very similar to the first script, with only maybe the definition of the trainer, where we give height, width, and channels instead of the in size, which was given for the MLP, because it was just the shape of the curve. Finally, for the parametric script, here we show that you can use our code to just generate your own version of RRAEDy, where you do some extensions, for example, add parameters. And to do so, you define a class with your own model. For example, here I defined the model that I called RRAE MLP with param, which inherits from RRAE MLP. So this is basically the rank reduction autoencoder with MLP that we use in the script. But I'm going to modify it a little bit. So what I did is that in my initialization, I'm going to define my encode MLP, because now I need to encode my parameters. And also an encode mix, which is the encoding of the concatenation. So if you remember, now we have an encoder for X, an encoder for P, and the small encoder for the mixture of both. So I define these, the encoder of the parameter and then the encoder of the mixture between them. And basically I say, when I say encode now, don't do just encoding like before. You will do the super.encode, which is the original function of RRAE MLP. This is going to take my X values. So it's going to give me my encoded X. I'm going to do a new encoded MLP, but this is going to take only the parameters and give me encoded MLP. Finally, I'm going to concatenate them, and then I'm going to say encode mix of both of them. So if you need to change the encode part, the decode part, the call part, you can do it all by doing this, by inheriting classes from RRAEs and then changing some stuff by yourself. As you can see here, the decoder is still the same. So I only did the mapping of the decode function, which is again maps the number of samples and the number and the time dimension for it to go fast if you go if you use it on TPUs or GPUs. But the only function I changed was the encoder, because we added the parameters in there. And otherwise, the script is very similar. The only difference is that we give here the parameter p as an input instead of only giving the input. And basically, it is expected in the call method here because, as you can see, we expect not only x, but also p. And so you can give x and p here to encode, and basically the encode function is going to deal with it like we said before because you modified it. So this is how the scripts look like. Finally, I will show you a small example. If you run the script on your PC, what you should expect. Basically, what you see here is what's going to be printed for every step. So whenever we pass a batch in the neural network and then we do backpropagation. And so we're going to see the loss, the Kmax value, and W, the matrix W. If you do not want to see this W because it's quite big, you can just erase it from here. But I keep it because sometimes it's useful to see how the convergence is happening on the W and how we get closer to the identity as our theoretical proof states. And so if you run script.mlp, so first be careful to be in the right folder. For example, here I am in RRAEDy and then RRAEDy because basically I have RRAEDy, and then I have my script. So be careful to be in the right folder to be able to run it, and then I'm going to run it by saying Python script MLP. And so now this is going to perform training for us on the Vanderpool example because we wrote Vanderpool here. If you go inside get data by pressing Ctrl and click, you can see that you have many options like circular Gaussian, it's the Gaussian that's rotating, the fluid example behind the cylinder, Berger's equation, mass spring, the parametric one, and the Vanderpool equation. Now, one more time, be careful on CPUs, it's going to be quite slow. Maybe here it's a bit fast because Vanderpool is a small problem. I strongly encourage you to work on GPUs or TPUs, whether on Mac or on Linux, because this is why we use JAX. And this is where it goes very fast. What's also good about RRAEDy is that since it's based on RRAEs, the library, you can just press Ctrl-C and it stops training and it saves everything for you. So right now, if I go to the terminal, let's say I'm bored of my training, I can just press Ctrl-C. And as you can see, it will find my training latent space, find my basis. And so it's going to continue doing its things normally. As you can see here, we got the errors because in the script, in the end, we printed the errors for the training and the test. So you can see that very quickly we got to 23 and 26%. If we would have waited 2 more minutes, I think we would have gotten the results of the paper. And also your Kmax here is 9, as you can see. So it is still fixed because we're still doing conversions. If you leave it for a bit longer, then Kmax is going to start decreasing and you will see the behavior of the loss where it jumps a little bit every time you decrease Kmax and then it goes down very quickly until the algorithm tells you, listen, this is wrong, you have to go back to the Kmax before. And so it will find the value of Kmax for you automatically. Now, if you don't want to use the adaptive algorithm, if you want to fix the values of alpha, you can come here and instead of using this generative, the general tracker, that will change the value of alpha, you can just use the fixed tracker here. And so replace this line by this line, and then you can fix the value of Kmax. It will never change. This was everything. Thank you for watching the video. And if you have any questions, don't hesitate to say so either in the comments below or on the GitHub repository.